Good day, everyone. Welcome to our topic now for discrete math, which is Boolean algebra. In this in this module or in this lesson, we'll be talking about the different operations in Boolean algebra. Then we will go to logic gates, creating simple logic circuits. Now, before that, here's a brief history of Boolean algebra. It was first conceived or first formulated or created by George Boole, or others would call it Georg Boole. Now, in his paper, which is entitled The Laws of Thoughts, which was published in 1854. After that, other mathematicians now show or improve or use the idea of George Boole in their next um, papers and um, undertakings. Now, for example, C. E. Shannon in 1938 showed how Boolean algebra or the basic laws of made by George Boole can be used in the design of electronic circuits, which we are now using, especially when we go to logic circuits. We will be able to appreciate the laws of Boole, or we call them Boolean algebra. Now, in comparison, we can compare the different Boolean operations in the other topics that we have discussed. Sets will be discussed in the next module, but we already have discussed logic, okay, the basic logical connectives. And this time we will be discussing Boolean algebra. In terms of the variable used in sets, we use capital letters or uppercase letters. In logic, commonly we use the variables p, q, and r. In Boolean algebra, we will be using the lowercase x, y, z. Though again, we can still use other letters in the alphabet, but the most commonly used variables or letters in Boolean algebra are the letters x, y, and z. In set operations, we have these: intersection, union, and the complement. In logical operations, we have conjunction, disjunction, and negation. And in Boolean algebra, we have these: the Boolean multiplication, addition, we call it ANDing, ORing, and NOT or negating. Okay, which means uh, the intersection, this one, the symbol, can be expressed this in this symbol in logic, and this symbol is just equivalent to this symbol in Boolean algebra. So this intersection is just equivalent to conjunction in logic and equivalent to AND in Boolean algebra. We also have special elements, an empty set and the universal set, and a false truth value and a true truth value for logic. And in Boolean algebra, we will be using 0 and 1. 0 means, if you compare it in a light bulb, 0 means off, 1 is on. Okay, let's start with the Boolean product, or the Boolean multiplication, which is represented by this dot. No? Also, you can also remove this dot, no, just write x, y. Just like in algebra, if we say x, y, that's just the same saying x times y. That, that is also the same with the Boolean product. Okay, if you recall our truth table in logic, uh, conjunction, if we use conjunction of two variables, you have false and false is equal to false. The conjunction of false and true is still equal to false. The conjunction of true and false is false. However, the conjunction of true and true is true. Same with Boolean product, Boolean multiplication. Now, if since f in logic is just 0 in Boolean algebra and t is 1, so which means 0 times 0 or 0 and 0 is 0, 0 and 1 is 0, 1 and 0 is 0, 1 and 1 is 1. So if you compare, now this is 0, 0, 0, 0, 1, and 0, 1, 0, 0, 1, 1, and 1. So again, the laws on logic and laws and the connectives or the operators in logic are just equivalent in Boolean algebra. So we also have the Boolean sum or the OR. Okay, this is OR. The previous one is AND. Okay, this one is AND. Just like in the logical connectives, we read this and this one as OR. And truth table for an OR Boolean sum is 1. So in Boolean sum, if ever there is at least one variable that is 1 or true in logic, then therefore the sum here will always be equal to 1, except when all of the values of the variables are 0, then the sum of that compound statement or the sum of those variables is just equal to 0. The next operator is the complement or the not. Okay, complement or not or negation. Okay. So the complement of 0 is 1, the complement of 1 is 0. Just like the complement of false is true and the complement of true is false. Now, in 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 logic circuits, if you recall that G.E. Shannon or C. Shannon used the Boolean algebra or the laws of Boole, to design electronic circuits. And the basic component or unit of gates, or for example, our CPU is composed of transistors, and these transistors form gates. Now, we call them logic gates. There are symbols, just like, for example, in electronics, resistor has a symbol. Okay, so logic gates has also symbols, and those logical operators have symbols. Now, so each logical operator has an equivalent logic gate. For example, the AND or the logic, the Boolean, the Boolean product has a symbol which is the AND gate. The Boolean sum has OR gate. The Boolean complement or the negation has NOT gate. Okay, so when we say a gate, so this is an idealized device implementing the Boolean function. Okay, the Boolean operations. It could have one input for negation, or it could have two or more inputs. When we say inputs, these are the variables that we are using. No? So this can be X or Y or Z or any other variable. So the variables are our inputs and produces a single output of our gate. Now our gate will produce a single output. Okay, in the truth table, So that's the last column. Okay, for example, you have x, y, and you are getting the product, the Boolean product of x and y. So this column here is our outputs. Whatever the values here, these are our outputs, which means that the left columns or the columns on the left, these x and y are our inputs. Here, no, down here, so it's 1 if you have 0, 0. So these are our input values. So 1, 0, 1, 1. And our output will be 0, 0, 0, 1. Again, the left side are the inputs, right side, okay, these are the outputs. Now this column represents the output of your gate. Okay, output. So same with the logic. So we represent the value of or the output of logic gates using truth table. So whatever the combination, so there is a corresponding output. So here are our logic gates. We have NOT. So the symbol for NOT is this one. So the NOT gate has one input. So if our input is X, so the output would always be the complement of X. Or we can write it as X bar or this one, not X. Okay, the negation of X. So the truth table, again, this is just a negation. So if our input is 0, then our output is 1. If our input is 1, since it's negation, our output is 0. So that's the behavior of a NOT gate or the negation. Next is AND or the Boolean multiplication. The symbol for AND is this one. Okay, so take note of this symbol. It's curved here in this part, in this tip. So you have two inputs. An AND gate can have 3, 4, 5, 6 inputs, but only has one output. So if our input values are x and y, input variables are x and y, so this is xy or x times y, x and y. So the truth table for this is this one, same with our conjunction. No, it's 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1 is 1. Then the next is OR gate. So this is the symbol for the OR logic gate. So again, remember that the left side here no, of this figure are the inputs. Can have x and y, and you have the output x, sorry, x or y. And the truth table for an OR gate is this one. So whenever there is at least one input that's equal to 1, so the output of the gate will always be equal to 1. Next is the NAND. So what is NAND? Now you take note of this. Okay, you have here AND. This is just equivalent to NOT and. What is NOT AND now? Recall this one. Take note of this NOT, which means AND is being negated. Now we'll be placing a NOT gate inside an AND. Okay, that's NAND. So just the negation, whatever the output of an AND gate. Now, a NAND gate has an output opposite to or in complement to the AND gate. So the symbol for a NAND gate, this is one. An AND gate which has a bubble. This is a symbol for negation. Now, commonly, the bubble is the symbol for negation. If you recall the symbol of NOT, you have a bubble at the tip. Okay, if you see gates, inputs or outputs which has bubble, that means those were being negated. So we have here A and B, for example, are our input variables. So this is Y, which can be expressed as A. Now, since A and B are being negated, so we can use expression AB bar or use a parenthesis and an apostrophe or parenthesis still and use the negation. Okay, these three here are just the same representation for NAND. And the truth table, as I have told you, is just the complement of the output of an AND gate. So if our inputs are X and Y, so supposedly an AND, no X, Y, as an output of 0. Since we are complementing it, so that is why it's 1, 0, this is 0, this is 1. So we just have to complement the output of an AND gate to have a NAND gate. Now, why do we have the NAND logic gates? In electronics or in creating logic circuits, they said that NAND and the other one are used to create, um, used to design and create combinational circuits. Seldom that they will use NAND, not rather, and or. Why? Because in your probably in your next courses, we will not discuss this one here. NAND gate can be used, no, a combination of NAND gate. When you combine NAND gates, it can perform an AND gate, it can also perform an OR gate, and it can also perform a NOT gate. So we call NAND and the other one NOR as the universal gates because they can be modified depending on which combination to use. A combination of two or more NAND gates. Now they can perform a another gate. Okay, they can perform the functions of the other logic gates. So going back, so again, this is the NAND gate. This is a truth table for a NAND gate. The next one is OR. Okay, NOR rather, and this is not OR. Okay, just remember the NOT term. No, N represents the NOT. And symbol for a NOR gate is this one, an OR gate which has a bubble. So same with NAND. Oh, NOR gate is just the complement of a NOR. Ah, NOR is just the complement of OR. So when we have OR gate, when we use OR, now supposedly this is 0, this is 1, 1, and 1. But since we complement the OR gate, we have 1, 0, 0, and 0. Okay, please remember these values, this behavior of the gates. Then we have XOR. So this is read as exclusive OR. Now, if you recall our logic discussion, so we have an XOR. Now, just a reminder or an information, I want you to check the truth tables or no, the logical connectives, the laws on logical equivalence rather. Check the laws on logical equivalence and the behavior of an XOR gate. An XOR gate is represented by the symbol, can be expressed as X bar Y or the complement of X multiplied by Y or by X Y bar. Take note of this property or this law on equivalence. This will be useful in your next topics or next in the next slides or next activities. Symbol for next OR is this one. Okay, you have here now just take note of the symbol. You have one OR, but you have here a curve here, and you will have an output x, x or y. And the truth table is this one. No, both both variables should not have the same values. Otherwise, if they have the same values, then the output of that gate is equal to 0. If they don't have the same values at the same time, then the output is 1. Then the next is XNOR. It's just a NOR gate which has a NOR gate which has a curve here. Or we can just say an XOR gate which has a bubble. Okay, so this is the behavior of an XNOR. Now, how will you relate an XNOR gate? Okay, an XNOR gate is just equivalent to by implication in our previous topic. So an XNOR gate is just the negation of an XOR gate. So the output will be equal to 1 if both inputs have the same values, at the same time. So for example, x and y are equal, uh, x and y are 0, then the output of that gate is 1. If they don't have the same values, x and y don't have the same values, then their output is 0. Okay, I have here some problems. However, we'll be focusing on these two. I will be just showing you these two. So I will leave the others to you. So kindly answer them. They might be included, or you might you might be required to submit the answers of these in your engage or evaluate activities. Let's solve first item. Okay, for a while. So let's proceed to the next slide. Okay, the instruction is to construct a truth table and a switching diagram of each of the following statements. So we have to make a truth table first. Now we can create immediately the switching diagram, but let's do the table first, okay, so that we will be able to know the behavior of this circuit. Sorry. Okay, let's have first the values of x and y. Though, again, for this time, you can go directly, since we have both negations here, we can evaluate directly x and y prime. But I would suggest that you place first or evaluate first the, say, the atomic statements, no? Those which don't have negations first. So we have here x and y, our atomic statements or atomic variables are x and y. So we'll evaluate the values or combinations of x and y first. So we have, remember that we will now be using 0 instead of false and 1 instead of true. So we have 0, 0, 0, 1. Or we can start here. This is 0, 1. Then you have 1, 1. Then negating x. So that's 1, 1, 0, 0. Negating y. We have 1, 0, 1, 0. Since this is sum, the rule for Boolean sum or is that whenever there's at least one value or one variable that has a value of 1, then the output will always be equal to 1. So here we have 1 1, this is 1, 1 0 is 1, 0 1 is 1, 0 0 is 0. So this is the truth table for this function or this combination. Now how do we create or construct a switching diagram for this. Now again, we have two inputs, so that is why we have X. Remember that these wires here are our inputs. These lines here are our inputs. Now what happened to X? It is being negated. So therefore, we will use the NOT gate, which has the symbol. Okay, and also Y is being negated. So we'll use this symbol. And after, we have the OR gate. So what's the symbol for OR gate? It's just like this one. Now, and the inputs will be placed here, and you will have your output. So this is X prime or Y prime. Okay. Or you can just say this is your function of X and Y. This is assigned as a letter. Say, for example, instead of function of X and Y, this is assigned as A is equal to X prime plus or X prime or Y prime. So you can just label it instead as A. Okay, as long as you know that A is X prime or Y prime. So this is how we create the truth table and especially the switching diagram for a given expression. Let's have the next one. We have the quantity of X prime, X or Z quantity, or X prime and Y. So we have three variables, the X, Y, and Z. Now you take note of the placement of the variables, which means X is the leftmost, followed by Y, followed by Z. Now take note of the arrangement of the variables. If it's written here as X, Z, Y, then we will have here X, Z, and Y. Now let's start with Z. So remember that the rightmost part changes its value in every step. So if we start with 0, then this will be 1. This is 0, 1, 0, 1, 0, 1. Then start with the second one. So this changes every 2 steps. No? So which means start with 0. This is 0, 0. Then 1, 1, 0, 0, and 1, 1. And at the end, as the last variable, the leftmost variable, it changes 4 times every 4 steps. So how did we solve it? That's 2 to the power of 2. So this is 2 to the power of 0. This is 2 to the power of 1. 2 to the power of 0 is 1. To the power of 1 is 2. 2 to the power of 2 is 4. So which means that x will change its value after its fourth row, or after the fourth row. So if you start with 0, so this is 0, 0, 0, 0. This is now the fourth. So the next one will be 1. No, it will have to change 1, 1, and 1. After, evaluate the x bar. So this is 1, 1, 1, 1, 0, 0, 0, and 0. Next, x or x prime and z. So remember, they should have different values so that the output of the XOR is 1. Otherwise, the output of the XOR is 0. Okay. Your x prime is 1, z is 0, so this means this is 1. X prime is 1, this is 1, 0, 1, 0 is 1, 1, 1 is 1, 0, sorry, this is 0. I'll erase this one first. Okay, 1, 1 is 0, 0, 0 is 0, 1, 0 is 1, 0, 0 is 0, 1, 1 is, 1, 0 is 1. Next, x prime and y. So x prime and y, you have x prime is 1, y is 0. So the result is 0 since we use AND. No, x prime is 1, y is 0. So this is 0. X prime is 1, y is 1. So this is 1. This is 1. This is 0, 0. Okay, then we have this 0 and this 0. After, so these two will then be ORed. Now we'll use OR, so which means whenever we see 1 with a value of 1, the output will be 1. So we have 1, 0, this is 1, 0, 0 is 0, 1, 1 is 1, 0, 1 is 1, 0, 0 is 0, 1, 0 is 1, 0, 0 is 0, and 1, 0 is 1. Okay, kindly check if this is correct. Therefore, this is our truth table. So we have 1, 0, 1, 1, 0, 1, 0, 1. So these are our combinations. 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, and 1, 1, 1. How do we create a circuit diagram for this? So let's start with recall. Now, always remember the laws of precedence or the priority. We start with the parenthesis, then the NOT gate. So we have inputs X and Z. Okay. However, X here is being negated. So we have X bar. And Z is being XORed with X bar. We'll have to put here. So this is now our X bar XOR Z. Okay. Then we have X bar and Y. Now, if you check your diagram, you already have an X bar. So you don't need to make an X here anymore. No, you don't need to have here X and just negate it. Okay, you can just tap. No, you can just tap to or from that X bar there. So how to tap? Just use circle, no hole. Then move it here. Since we use AND gate, we'll have an AND gate. Okay, and Y. So this is now your X prime and Y. Now, as you can see here, I just put a node or a point here that this is connected. The ideal one, now the ideal tapping is putting here this point here. Then when you encounter a wire, you have to jump since they are not connected. So jumping means the wire is not connected to Z. Okay, again, this is the ideal way of making circuits. Okay, you place here a tap, meaning you are tapping from this line and you are jumping. No, you don't want to connect to Z because in real life, when you just place a wire there, no, something might happen. Then the OR gate. So we can have this since so that we can create a smaller OR gate. So this one and this one. So we now have an OR gate. So this is now our f of x, y, and z, or this expression here. So this is how we create a circuit diagram. Now again, recall the previous slides, the previous items, answer them. They might be included in your activities. Let's proceed now to the laws of Boolean algebra. Just like the laws of equivalence, we have laws on Boolean algebra. You can still refer to the laws of equivalence because they will just have the same answers. No, the laws do not change. So we have here commutative, associative, distributive, identity. We also have inverse, involution, idempotent, De Morgan domination. Next, we have absorption. Now, these laws, just like in laws of equivalence, are used in simplifying expressions. So in logic, we use laws of equivalence to simplify compound statements. So also in Boolean algebra, we use it to simplify expressions. For example, this one. How would you simplify this Boolean expression? So recall the laws. What do you think is the answer for these? Now, I want you to recall those laws, okay? So I will be presenting to you the answer. Now we can use, since we have the same operations, and or rather, we can use commutative and associative. Remember that we can only use commutative and associative to terms or expressions or groups which have the same operations. For example, this one. No, we cannot use commutative to or associative to x bar x or x prime y. Okay, since this is using in an operator, so instead we will treat this as one. Okay, then we will um, use the two laws, no? Commutative and associative. Then after we have law for this, okay, we can also use a law for this one. What do you think are the laws used for x or x and the law for x prime y or y prime? Okay, the answer is first. Okay, we'll start first with this one. We have idempotent, and the second one is distributive. Okay, then simplifying further and further, and then we have one. So this very long expression here is just equal to 1. So that's how we simplify a Boolean expression. There's an alternate solution for that. Now you have here, we use first distributive, no, to this group. We will not use the associative and commutative, so we will use this. So distributive, then we'll get this expression. Then using the inverse law, we'll have one identity, and then commutative and associative, idempotent, then inverse. No, this is idempotent, this is inverse, then we'll have one. Okay, they will just be resulting to the same answer. So this is equal to one. As long as we use the right law, the right laws, we will be arriving at the same answer. So whichever laws we're using, no, the answer would always be the same. So just like the previous one, no, it has different approach. No, you may also have a different approach, but you have to make sure that you are using the right, no, or the appropriate laws. Okay nga, dili mo buhat-buhat ug inyo. You just follow the tables, okay? The laws on Boolean algebra, and also you can refer to the laws on equivalence. Oh, sorry for that. I have shown the answer. Okay, now this is your task. I want you to, I think this is almost similar to the previous example. Now, I want you to use or the different laws of Boolean algebra and check if you will arrive to this answer. The answer is just equal to y prime. Next, using laws. Now, when we have combinational circuit, we will be using the laws to simplify the circuit. And after, okay, wait, wait. Sorry for that. Okay, so I want you to use the laws of Boolean algebra so that you can arrive to this answer. Next, now the laws of Boolean algebra are used to simplify complex circuits, combination of circuits. Then after, we will be trying to create circuit diagram, just like we did in the previous one, creating circuit diagram for an expression, logical expression. Now, a logic circuit is um, connection of different gates. Commonly, we call it combinational or combinatorial circuit. Others would call combinatorial, but most books in logic circuits and switching theory use this term combinational. Now, it's constructed by combining different logic gates. And commonly, that is when that expression is or cannot be simplified further. So if it can be simplified further, the better. Okay, the lesser the number of gates, the better. Here's an example of a combinational circuit. Now using different logic gates. Okay, you have here inputs P, Q, and R. So it's being negated, and you have not. Then you have this and this one. So this is the output. Okay, the quantity of P and not Q or not R. So if you will use Boolean algebra, this is just P and Q prime. This one is P, Q prime, or R prime. You can also use P, Q bar. This one will be P, Q bar, or R bar. Oh, they're just the same. Okay, so here's an example of just logic circuits and its equivalent truth table. Check. Just check with these. Then we have here an activity. We have to simplify this expression and draw the simplified logic circuit. And how do we do that? Oh, this is your activity. The answer is X or Y prime. Okay, now check your the next part of this module, of your module, and try to answer or show your solution for this problem. Again, use the laws of Boolean algebra so that you will arrive at this part here. And a hint is that remember what I have told you in uh, XOR. Okay, remember what I have told you in XOR. For a correction, just a correction. This is not the problem. I think I was not able to change this one. This is not equal to x plus y prime. Okay, okay, I'll just erase this. I'll just change it in the slides. Okay. Now the problem is not this one. This is actually because this is just almost similar to the previous. This is x, y, x prime, y prime, and we'll remove the prime here. This is just equal to y. And we also have x on the outside. Okay, so that's um, okay. This will be your next activity. Now prove that this whole expression here is just equal to x or y prime. And draw the simplified logic circuit. And that would be all for this discussion. Thank you for listening and see you on the next discussions.